So in this section, we're going to be looking at the physical properties of solids. The first thing that we're going to talk about is something referred to as vapor pressure. And again, so you can think of it as pressure. It's how much gas actually forms from a substance or the tendency of that substance to go into the gas phase. It's not as large of a property in solids as it is in liquids. But the general truth is that if a molecule has weaker intermolecular forces, it's going to have a higher vapor pressure because those particles are not held together as strongly, and therefore they can escape into the gas phase. And the gas phase, again, is a phase that has very little order and no interactions between particles. And so the example here that's shown is mothballs, which I don't know if you've ever smelled that. It's not the greatest smell, but this solid, some of it goes into the gas phase. And whenever you smell something, you have to get molecules of that into your nose. And so it has to go into the vapor phase. Iodine does this as well. Um, I'm not exactly sure what they're showing here. Probably dry ice is what's being shown in this diagram, just to indicate going from a solid directly to a gas. And so, when you look at a question like this, we're at negative 125 degrees Celsius and we've got two solids. And the question is, which is going to have the lower vapor pressure at that temperature? Okay. And so the compound with the lower vapor pressure would have the stronger intermolecular forces. That seems a little bit backwards. But again, if there are strong intermolecular forces, the particles are being held together more strongly. They're going to have less tendency to go into the gas phase. So if we look at these molecules, CHF3 is going to be polar, and CS2, because it is linear, is going to be nonpolar. So CHF3 is going to be held together by stronger intermolecular forces and therefore have a lower vapor pressure. So that's how you would attack a problem like that when you're dealing with these types of solids. So melting point, you're familiar with what melting is. It's the phase transition from solid to liquid. And so the melting points are essentially a measure of how strong the intermolecular forces are. If there are really strong intermolecular forces, that melting point is going to be higher. And so what you notice, and I showed this last chapter, that things like water, ammonia, and HF have relatively high melting points, and that's because they have very strong hydrogen bonding. Okay, so very strong intermolecular forces are increasing the melting point of these substances. Okay, and so again, the stronger intermolecular force is that a substance has, the higher the melting point that substance is going to have. And so this is just a table showing this, where you can look at a variety of different substances. You can see the molar mass, and you can also see the melting points. Okay, now in general, what you notice is ionic bonding has very high melting points. Okay, and so that those are usually the highest. Okay, if you have a variety, so in this case, this has dispersion, dipole-dipole, and hydrogen bonding. So this is a sugar, um, and that's going to also have a pretty high melting point. Water is 0 for its size. It has a relatively high melting point. Helium, again, just an atomic substance which just has dispersion, has a very low melting point because that is very weak intermolecular forces. And so that, connecting intermolecular forces to melting point is an important key to this type of discussion.